students, and welcome to computer science class. In this class we'll be talking about alternative logic gates. Under alternative logic gates, we shall be discussing the examples of alternative logic gates. We shall be representing the types of alternative logic gates, and we shall be representing it in a logic gate and also in a truth table. Initially in our previous class, we emphasized on logic gates, where we said that there were two types of logic gates. We said there were standard single logic gates and alternative logic gates. In that class, we discussed extensively about the standard single logic gates. In this class, we'll be talking about the alternative logic gates. But just to have a brief recap on what we discussed on standard single logic gates, we talked about their examples. We emphasized extensively on the AND gate, the OR gate, and the NOT gate. We said the AND gate is a gate that produces an high input if all inputs are high, and produce a low output if either one or more are low. We talked about the OR gate and the NOT gate. But in this class, we'll be emphasizing on the alternative logic gates. That includes the NAND gate, the NOR gate, the XOR gate, also called the exclusive OR gate, and the XNOR gate, also called the XNOR gate or the exclusive NOR gate. In the class, we'll also be breaking these four gates in brief. But let's take on the first one, called the NAND gate. The NAND gate simply states that it is a combination of the AND gate and the NOT gate. What does that mean? It means to get a NAND gate, you must first of all get an AND gate like you have in the diagram and combine it with an inverter called the NOT gate that produces the NAND gate. The NAND gate also is a gate that states that the output will be low when all inputs are high. On all cases, you will only get a low output when all inputs are high, but you would get a high output when either one or more are low. Similarly, it can be represented in a truth table. In a truth table, three input signal, we are having A, B, and C that represent the numbers of gates. Looking closely, you would see that A has 1 in the first row, B has 1 in the second row, C has 1 in the third row. The next row, you have A and B and C giving you 1, because the law for AND gates is all expressions needs to be high for the output to be high. But in getting your NAND gate, you have to navigate, or you have to invert your AND gate. That's the reason why the final answer is 0. Similarly, when all inputs are high, it gives you 0. Also, you have your NOR gate. What does the NOR gate state? The NOR gate states that it is a combination of the OR gate and an inverter. It means an OR gate that is being inverted. What does that simply mean? It means that when all expressions are low, the output will be high, just like you have in the diagram and in the truth table. All expressions needs to be low for the output to be high. That's the reason why you're having 0, 0 giving you 1, because 0, 0 is low. But in the next gate, called exclusive OR gate, or also called XOR gate, and also called XOR gate. It is exclusive because it states that the gate or the output of a XOR gate will be low. When I say low, I mean 0. Will be low if all inputs are the same. I come again. The output will be low if all inputs are the same. Similarly, the output will be high if all inputs are different. That's the reason why you're having 0, 0, giving you 0, 1, 1, giving you 0. It can also be represented in a 3-input truth table and not just a 2-input truth table, having 1 A, B, and C. Under A, the first row, you're having 1, the second row, 1, and the third row, 1, giving you 0. Why? Because all expression in the input gate are the same. Take your mind down to the very last row, where you have 0, 0, 0. Giving you what? 0. Reasons? Because they are all the same. But when they are different, they are no longer 0, but rather they are 1. Moving forward, the exclusive NOR gate. People will say the exclusive NOR gate is the opposite of the exclusive OR gate. That is very true and very, very correct. But I will add to that definition, or I would add to that law by telling you that it is not just the opposite, but there is an introduction of a NOT gate in it. Because by the time you combine an exclusive OR gate with a NOT gate, it gives you an exclusive NOR gate. Similarly, you can define or state exclusive NOR gate as a gate that will produce an high output if all inputs are the same, and a low output if all inputs are different. Moving forward, looking at the truth table right before you, in a 3-input gate having A, B, C, you would see that you have 1 for A, the first row, 1 for B, second row, and 1 for C, the third row. And from what you can see in the next row, having 0. Why? Because what happened is they first of all performed an exclusive OR gate, and then they inverted it to give you an exclusive NOR gate. So therefore, it answers the question that states that it is a combination of an exclusive OR and a NOT gate. Looking at the diagram briefly, it takes us on how well we know all our logic gate diagrams that runs from AND or NOT, NAND, NOR, XOR, and exclusive NOR. All of these are the diagrams, and it doesn't change. It remains the same in the past, it remains the same now, and it will remain the same forever. There is something unique about these gates. Very soon, as the class progresses, still on this module, you would see something unique about it. But before then, let's take a look at this example. You're having Q as the output to be gotten if there is a combination of A and B into the brackets plus a combination of A naught and B naught, or A or not A and not B. In doing this, you would see that there is a combination of AND gates and OR gates and NOR gates. All of this makes up the diagram. Now, from what I told you earlier on, something unique about these gates, they are also grouped into three. Now, it's not like the standard and the alternative. They also group into three, where AND, NOT, and OR comes under the basic logic gates, universal NAND and OR, and other. Thank you, and God bless.